Hey, welcome back. I am just checking our stream, making sure that we are ready to go. Oh, wrong place. Let's go live, or I can go to my channel, right? So it says we're live. I'm gonna check my audio video stream, making sure that we are ready to go. And it looks like we're up and running. Cool. So, last time on dynamics, on our advanced dynamics, we were taking a look at this damped pendulum and what the equations of motion were. I went through in this video and figured out what the equations of motion were just by using Lagrange equations. And then in this notebook, I go through the same process, but rather than rederiving all the math, like actual taking derivatives and partial derivatives, I use the symbolics to look at what the output would be. So hopefully you've been able to take a look at this and see how it looks. Like, does it match with what I did in the video, like in these notes? So the next step is trying to actually, because this is giving us something that has an equation of motion where this is true for all time, and it relates the position. Here, if we're coming back up here, it relates this x position, this angle, the velocity in this x direction, the theta dot, so how fast it's rotating, all to the accelerations. And in this case, we have these 2 degrees of freedom, and we're solving for that. Next, what I did was I took this end result, and because it's a math equation, I can copy it as a LaTeX command, and AI is pretty good at reading LaTeX. So let's see. It's trying to help me. It's trying to do some simplification, which I didn't really want it to do, but that's all right. And now it is loading some stuff, and I just want to see if this is actually working. So I do want to add viscous damping, but I don't want to add it to the theta dot term. I don't want a viscous torque. All right, so let's see what happens if we just grab this code and try to run it in here. And we might as well start with a new notebook. And what I like to do is put everything in commas here. So we'll load that stuff up, and while that's loading, I'll come down and grab this next block of code. Tab that over. I don't love this length L, but that's okay. And what I did here is I'm telling Julia that I want to use modeling toolkit in particular. I've been playing around with this toolkit. It's really cool. The neat part is that we can define like variables and parameters and use actual like equations of motions this way rather than. So we should be able to kind of go straight from a Lagrange definition, like kinetic minus potential, take some partial derivatives, and then turn that into an actual ODE system. So I'm playing around with, this one's kind of an intermediate step where I took the output from those two equations, the couple of equations, pulling it in here. All right, so I have a simplified structural simplify, and let's see what this one does. Add this one in, paste it. And, oh, it's probably going to complain because I should have it as a beginning and end. It's still loading. And I've talked about this with some people. If you've had a chance to like meet and go through some code together, Julia is super fast. It's one of the fastest programming languages I've ever used, other than like straight Fortran or C++. It's amazing how fast it is for such a readable. And I say readable in the sense like if you understand the math that you're doing, then you can understand kind of the Julia code that you're looking at. But it has a long startup time. So all this like the pre-compiling steps, that takes a long time, and there's not much we can do about that. It's in order for this thing to run as fast as it does, it needs to do these pre-compiling steps. The amazing part is that we can take this code and kind of expand it. So right now I'm running it on a laptop that's not particularly impressive. It's got enough memory, but if I take this same code, dump it into a supercomputer, we don't need to make really any changes. Like Julia can run on supercomputers, and we can scale up the analysis that way. So that's why we're kind of using Julia for these systems, even though you have to learn a new language, but it is really cool. We can do all sorts of cool stuff with it. And I do really like the animations that you can make with Julia. That's been one of my favorite parts. All right, so let's see if we can actually plot something. And it's loading. It seems like it's going pretty well. It's just getting a little hung up. Still in the pre-compile. Oh, in the package management. Sometimes I run this beforehand so we don't have to watch it just loading while we're streaming, but I didn't do that today. Sorry about that. So while it's loading, let's take a look at what we are actually dealing with. So we've got pendulum equations. It looks oh, it's simplifying this equation. So it's trying to turn it into a 1 degree of freedom system. I don't love that. But it still has an X double dot. Yeah, so what this one is doing is it's ignoring the fact that I want a 2 degree of freedom system. This is kind of annoying to me because that's not at all what I wanted. we'll let it run, but I'll show you what the difference is here. It's almost done. What? Angle theta not defined, but it is defined. Base acceleration. Oh, I see. Yeah, that's... So what Copilot did on our behalf without actually telling us, I mean, it explained it, but it also gave a whole bunch of, like, it was an info dump of stuff. Was assuming that we could control what the base acceleration is, which I don't like that. I didn't want that. So let's see if we can. This is not right. I want the base motion x dx ddx to be degrees of freedom. And then angle theta, why is angle theta not defined? Probably because this one is not defined. Why is it saying this? Do we even need this? It's taking too long. I don't know why it's... Alright, so now it's actually creating an equation, a pendulum equation. And full system. So this is what I had wanted. I wanted a theta and a theta dot x and a vx. Why is it recreating my damper base? I already gave you my equations of motion. So the thing here is that I don't think we'll have, I mean, it will be an ordinary differential equation, but it's not going to be a linear ordinary differential equation. that's loading up. Let's just grab our notes from last week. What? Oh, that's not it. Here we go. Let's check back in on here. See, it's still trying to turn it into a single degree of freedom problem, but we don't need to do that. All right, so let's scrap Copilot because it's not telling me what I want to hear. Let's go back to I know this equation of motion, so let's delete this stuff. Delete. We're going to delete this and delete this. We still have modeling toolkit. We still have that. So my mass matrix is going to be m times L times cosine of theta, and then m times L times cosine of theta, and m times L to the third over 3. And this is a function of theta. So let's say pi over 2. Oh, and m is not defined. Let's say m equals 1 here. L is not defined, and we'll say L equals 1. Oh, whoops. I need lowercase m's. Alright, so when I have 90 degrees, cosine of 90 is 0, and I end up with 1 for 1 kilogram, and then ml cubed over 3 ml squared is then 1 times 1 over 3, 1/3. Cool. That's like this matrix over here. That's going to help me for when I'm trying to define function. Getting started. So I want to define my equations this way. So if I have two connection equations, let's see. First order lag system. System EQs. So here's my equations, time. So I think for the most part, what I'm trying to do is create these equations. It's the same down here. What are these derivatives? Okay. Weakly nonlinear oscillator. Yeah, I know, I'm just sort of reading through some of this stuff. Alright. Create function for ODE integration. Optimizing differential equation code. Let's call this Y. This one's Y. Then we have parameters, which will be M and L. And then time. So in our case, we're not trying to say this, we're trying to say M of Y and theta d theta x dx. Actually, I kind of like to keep these together, like theta x, so then I can have like y is my state variable derivative, so theta x d theta dx. m of theta slash right hand side, and this is going to be 2 through 3 to 4, pretty sure. I'm doing this to set up that the change in theta and x is d theta and dx, and then the change in d theta and dx is the acceleration, where my right hand side is everything over here. So it's going to be, or I guess not that one. I'm going to use this full one. Like that. So the first equation is a negative b times dx and plus a k times x. Minus kx, and then plus m times l times dx to the second divided by, and then times sine of theta, and that one's a positive. All that's equal to 0. And then our next equation is 0 theta dot, 0 theta, but then an m times a negative m times g times L over 2 times sine of theta. And I don't need that second one. And now whenever I have this m to solve for x double dot and theta double dot, I'm going to turn it into a linear algebra problem where this whole thing turns into a vector. I'm going to, and then return nothing. So that this one should be okay. So instead here, I'm going to say this is pendulum. 0, let's go with 0 to 1 second. How do I give it? My initial condition. I think that initial condition is here, right? And for initial condition, let's say pi over 3, 0, 0, and 0. Just some initial angle, but then no initial speed, no initial x position. Pendulum is definitely defined because I just defined it. Did I not? Did I make a typo? It's absolutely there. What am I doing wrong there? Why is it telling me that pendulum is not defined when it is absolutely defined? Oh, maybe I need the exclamation point. Oh, I don't have an A, do I? That one should be my parameters. So 1 and 1. Alright, so that's making a little more. Oh yeah. Those are equal to y. G is not defined. We can define that. I know what it is. We're here on Earth. Row 2 is mismatched elements. Oh, that's okay. Just get rid of that space. This is something kind of weird about like creating these matrices in Julia is spaces are new rows. So sometimes, like in this case, it's working. Or sorry, spaces are new columns. But I can't. So if there's mixing and matching spaces, we might end up with problems. And zooming in a little, realizing that a little small for us, huh? So we'll get rid of that space, and that should. All right, look at this. We're getting some answers. I think if I'm .u, there we go. What? Got 1 through 56. That's what I want. 56 answers. I want to plot it. Oh, what? I don't want that. It's showing me a whole bunch of those. All right, so now I'm starting to get a little closer, huh? Okay, so now I can see time versus angle. I'm pretty sure this is the angle. Starts at 60 degrees and goes up to 120. That's a little strange, so probably I'm missing a minus sign. I mean, it looks okay. Let's go over to like 5 seconds. Well, we'll go to 10 seconds. And the original goal here was trying to figure out, can you damp the motion of a pendulum without actually like grabbing onto this thing? So can we model what damped pendulum motion looks like just based on how this support is moving and what forces are applied there? And then also, can we create damping there? Come on, update. I need some updates here. But it is getting stuck. So this is kind of what I wanted to show. I'm having some trouble. I'm not sure why. But going from, like, once you do all this math and you get it to a form of like, all right, now I have this differential equation, I want to solve it. One way is kind of it's great engineering process of like just linearize the whole system, turn it into a linear set of equations. And those are nice and solvable. You can build control systems with them. I was trying to show like how we can use numerical methods to actually solve this problem. And this is the general way of kind of doing that. It's like I have this mass matrix. It's like 2 by 2 m. And then I have these equations describing the acceleration. So I can take this m, it's a function of theta, and solve for those x double dot, theta double dot. Oh, that's why. That is silly of me. I switched the equations, didn't I? So really, this should be a dx. This should be a d theta. This should be x, and that should be theta. That was very silly. I should recognize my own system of equations, right? All right, so that was one of my problems. Let's see how this. Come on, why aren't you updating? Why is it only going to 0.3 seconds? should be looking at number 2 to see. And this should be a 0 and a pi over 3, like that. I'm still not getting to 10 seconds, so let's take a look at the live docs. Usually there's an example, U0, so there's my Y0, and here's my time span. And I'm plugging that in. Let's just look at the first 2 variables here. So for some reason, it's not showing me singular exception. Oh, if m of theta becomes singular, then that could be a problem. And that might be happening because I'm not actually plugging in those values. Maybe it would help if I just move this. Say m is 0.5, L is 0.9, just so it's not 1 and 1 here. And then instead of making this a function of all that stuff, I'm going to do this. And now I don't need to plug in that stuff. I'm still getting pretty small time. Like I'm only going to 0.05 seconds, which... Oh, and now I don't need those parameters, huh? I guess I can leave them. Oh, weird. What? How is the parameter affecting... Oh, because I'm plugging in the M here. Can I just do this? So this has 4 values in it. Two-element vector. Wait a second. du, u, p, and t. Alright, so let's try some AI. So I'll show AI the function that I came up with. Let's make a new chat since it was not helping me. Here is my ODE. I am plugging into ODE problem and solve. Help me set up the inputs for t equals 0 to 10 and y0 equals 0 pi over 3, 0, 0. T-span. Yeah, I already have that. I already have those. So maybe this is all I need. Now, getting this error. Getting this error. Why? Try again. Alright, so I need to add a parameters in here, even though I'm not using it. And then I get something, but it's not the right time span. It's still a very short time span. It is decreasing, which is what I want it to do. My guess is that my so I could use a different solver. Stiff capable. Let's try this one. still only giving me return code is unstable. It shouldn't be like completely unstable unless I have some kind of error in here. Negative b dx, negative k times x, dx squared sine theta. Question is this thing sometimes, does the determinant equal 0 sometimes? Like, does it become a problem? Well, that would explain some things. So for some reason there's a very unstable, which that one, this doesn't make sense to me, that it's so unstable in velocity, but meanwhile position is fine. Like, there's no infinite velocity here, and it should be oscillating. But for some reason, when I look at the velocity, I start at 0 and then I get to somehow 3,000 meters per second squared. Maybe I am not assigning these correctly. I mean, I think that's fine. The velocity terms are unstable in this solution. What's wrong with my function? I mean, maybe that's singular, but I really don't think so. Your forcing term is mechanically inconsistent. Is that true? It does have a Coriolis term. Real concerned about this mass equation. Here is the mass equation. It's not singular, and this is a cart pendulum. I don't think it's singular. All right, singular 1/3 minus. So when it's 54, so let's just change this to like pi over 6. Then it should never get to that. Yeah, why is it increasing now? Should this be a d? Oh, this is a d theta squared. How did I miss that? ml d theta squared times sine theta. Well, that was silly. It didn't help this problem, but that should... ml theta dot squared times sine theta. So that looks right. Inconsistency in gravity. Why is that? But I don't have a mass of the cart. The cart is 0. And I could try that. Just add a little mass to the top. I don't think it's really going to solve any of the problems that I'm seeing. You know, I'm not sure what's happening. So I'll keep playing with this, and then I'll come back with, so at least getting started. We know we can take the differential equations that we have, plug it into a function like this, and then through some work, it's not always like a quick, hey, here's the answer, but with some work, we should be able to get like a numerical integration here. Right now, I'm running into this problem where for some reason it's like, yeah, just taking off, where all of a sudden I have regular velocity, then all of a sudden the velocity becomes yeah. Yeah, something makes it shoot off, where it keeps making smaller and smaller time steps, but the velocity keeps getting higher and higher, both for x and for y, which is strange. But I'll keep working on it, and I'll come back to you soon, and then we'll figure it out. Cool. All right. Thanks for joining. Hopefully this was helpful, at least seeing like how to take math, turn it into some code, and start to get some insights, and even troubleshooting kind of helped me kind of analyze each of the pieces of the things that I was working on. All right, so I'll be back, and I'll catch you there.